because I think Jess.
All right.
Did you commenting on the thing last night? Okay.
So, how's everyone? Good? You guys really do seem more energetic than normal. Fall break? Fall breaks in 2 weeks. Almost fall breaks. Almost.
I don't know, I probably took the had 3 cups of coffee already.
Yeah, I have cold brew.
But
Okay, all right, we're good.
I don't know.
Okay, so coming up, the chapter 5 homework I currently have set as being due next Friday, so that would be October 11th. I know people have asked me about that. Yes, that's the one you're working on right now. There is a chapter 6 homework, which is the next chapter we'll go through. That one I think I have set due as the day of the exam, which would be October 16th. Sorry, people are looking at the notes. It's not that I didn't want to give another, like a whole week to do that one, but if I make it due on Friday, it's due, first of all, after the exam, which seems silly. Why would you practice all of this stuff after an exam? And it's the Friday of fall break, so I would rather not have homeworks due over fall break. So I'm going to leave it like that. I would encourage you to turn in the chapter 5 homework early. If you want me to move up the due date, I can, so that I can get it graded faster and back to you before the exam. It's sort of up to you all. Yeah, so I could make, if you want, if it would help, I could make chapter 5's due next Wednesday, and then chapter 6 due the Wednesday of the exam. Is that better? So 5 would be due Wednesday. I know some people are not happy with this. Okay, how about if you turn it in by Wednesday, I guarantee that I'll have it graded if you wait until before the exam. If you turn it in by Friday, which I'll make the official due date, I will try and have it graded before the exam. But I'll also post I have an answer key. Oh, no. I also have the answer key, so I'll post the answer key on Friday, so if I don't get everybody's graded by Friday, you can at least look at the answer key and make sure you're doing. But I'm going to leave chapter 6 due on the following Wednesday, so if you turn in chapter 5 later, you'll have to be a little bit more rushed in chapter 6. I'll make it your choice. I'll encourage you to turn it in early, but I'll do that this Friday. If you downloaded the chapter 5 worksheets before Tuesday, it may be incomplete. So I was writing the answer key and I realized that I left off an A, B, and C on question 2. So if you printed it and it does not have A, B, and C, I can see one already that doesn't, go back and you can just, you don't have to reprint it, but just make sure because there's no actual question there. A, B, and C are the questions. Does that make sense? So like number 2, if you printed it too early, it's just a question. It's just a setup with no question, so there's nothing to answer. Okay. So go back and look at those if you, just so you're aware. Okay. Yeah, and then exam 2, which again is just on 2 chapters, so it's shorter or less material than the last one. It's on linkage, mapping, and chromosomal alterations. So we'll talk about those next week. It is shorter than the last exam. The questions are less applied than the last exam. So I'm expecting big things.
Please don't.
Don't expect big things?
Expect the worst and hope for the best.
There's that pessimism again.
No, that's realism.
You all are smart, you're capable, and I have confidence in you, so. All right. Yes, you guys got this. Okay, so we're going to keep going with crosses, and we're going to start looking at how we actually map across, or map linked genes on a chromosome. So we ended talking about what our progeny look like, and I'll remind you here that when we're looking at the phenotypic outcome of a cross, and we think that there's linkage, first we would test for linkage by doing that chi-square, right? Knowing that this is not our expected 1-to-1 to 1-to-1 ratio, which is what would happen in independent assortment. But after we get to that point where we think these genes are linked, we can start picking apart which ones are the parental phenotypes and which ones are a result of recombination. So in which offspring do we actually see the result of that crossover? And the easiest way to do that, and we'll come back to this kind of over and over again, is by kind of classifying them. So the first way we classify them is by just looking at parental phenotypes and phenotypes of the offspring. So here is one parental phenotype, normal leaves, tall plant. Normal leaves, tall plant, so that's one parent. Mottled leaves, dwarf plant, mottled leaf, dwarf plant. These two phenotypic outcomes in the offspring are not parental, right? So we have dwarf plant with normal leaves, that's one character from here and one character from here. Okay, so we get a crossing or a combination of the two paired phenotypes. The other way that we can kind of verify that is by looking at the proportion of offspring with the different phenotypes. So we can group these two together because they are the largest proportion, smaller proportion. Right? So we only have 7 and 8 individuals that are recombinant and 55 or 53 plants that are parental. So our next piece of math is figuring out how frequently the recombination events occur. So how often do we get crossing over between these two linked loci? So we know that these genes are on the same chromosome and they are physically linked together. We know that because we saw it in those offspring. We can calculate how often crossover occurs between these two genes with this equation. So we're looking at a recombination frequency. We take the number of recombinant progeny, or progeny means offspring, over the total number of offspring in that group. And then because it's a frequency, we multiply it times 100. So if we want to do this, I'll write this on the board. There's our equation. If we want to calculate the frequency of crossing over between these two genes, so between our M and D genes, there we go. It's blurry, but it's okay. So if we wanted to calculate the crossing over frequency between M and D, how would we do that with this equation? Okay, let's start by adding up the total number of offspring in this group. Okay, so our denominator is going to be simply add all of our phenotypic classes together, so all of the offspring. The numerator, or the top number, is 15 because we add just our recombinant progeny, which we've already identified as being these non-parental phenotypes. So that ends up looking like 15 over 123 times 100. Somebody math me. 12.2%. Does everybody get that? Yes? Okay. So the frequency of recombination, or the frequency of crossing over between the M and D gene on this particular chromosome, is 12.2%. So 12.2% of the time when you're forming gametes, you will get a crossover event between those two genes. That means that 12.2% of our offspring are recombinant, over 12.2% of the time. Now this will never go back to normal. Oh my gosh. What? Okay, so with this number, we can now construct a map. So oftentimes when we're doing these problems, we see in the offspring that we have this sort of non-Mendelian looking inheritance, right? We see a deviation from our expected. We theorize that that is because the genes are on the same chromosome. We can figure out how often recombination happens, and using that calculation of frequency of recombination, we can also determine how far apart on the chromosome these genes are. So we can actually map them on a chromosome. So our recombination rate or frequency of 12.2, we simply convert that into what we call map units, or we also call centimorgans. So there are many ways that we can sort of say the same thing. For every map unit or centimorgan that we calculate between two genes, the recombination rate is 1%. Okay? So if we were going to map our M and D alleles on a chromosome, it ends up looking fairly simplistic. There's our chromosome. There's our M allele, or our M gene. There's our D gene, or D locus. We know that recombination happens at a frequency of 12.2%. We convert that into map units. It's a very easy one-to-one conversion, so it's not stoichiometry or any sort of fancy, don't say, is that a dirty word? Recombination. See, I can't even say it. Okay, so we simply do that, and we would label this. I'm fine with if you label this as centimorgans, which is a little C and a big M, or as map units, which is an M and U.
Wait, so is it between them and is that what you're saying?
Yeah. So the distance between these two genes is 12.2 centimorgans or 12.2 map units. Whatever you do, give me some sort of unit. Right. It's not 12.2 nucleotides. It's not 12.2 centimeters. It's 12.2 centimorgans or 12.2 map units. Okay. So your units are important as always. Alright, so I realized that I just showed you a two locus cross there, or two locus interaction, right, just M and D. I think we'll look at one or two more examples with just two loci, but then we're going to head into 3-point crosses, which would be what are shown up here with A, B, and C. For our class, we will not go any further than 3-point crosses, but in research, we use this sort of method to map all of the genes on a chromosome, which could be hundreds of genes. Okay, so we are mapping all the different distances between and the order of all of the different genes that we have on a chromosome. So we could go beyond it, but you know how when we go from 2 traits to 3 traits in a Punnett square, and we go from 16 to 64 blocks. The same thing happens here when we're looking at phenotypic classes. So if we look at 3 genes, we have 8 phenotypic outcomes. If we're looking at 4, we would have like 32 outcomes. So it just gets to be too much. So stopping at 3. All right, so now that we've talked about it to this point, there are 2 really important caveats that I have to make with mapping and linkage. If we have 2 genes that are really far apart on a chromosome, we cannot use our methods that we've talked about so far to determine or distinguish between those genes being linked and those genes being on a different chromosome. So the further apart any two genes get, the more difficult it becomes to determine if they are actually linked or if they are on different chromosomes. Okay. So we can kind of look at our recombination frequency math and think about our phenotypic classes to talk about this. Right now we're at 12.2%. If this number goes up to 25%, what would the ratio of our phenotypic classes be? Okay, so for this one we had sort of 50 individuals in each of the parentals and then 7 and 8 in each of the offspring. If we're just doing this out of 100 offspring, and this rate is 25%, what do the number of offspring look like? So we have 4 phenotypic classes. I'll call them parental 1, parental 2, and then recombinant 1 and recombinant 2. We have a total of 100 offspring and a recombination frequency of 25%. So 25% of those 100 offspring are going to be recombinant, 75 are going to be parental. Okay, great. So we have a combined total of 75%, or even 75 because I'm making out of 100. So 75 will be parental, 25 will be recombinant, and excuse me, we should assume equal numbers in each of the parentals and equal numbers in each of the recombinants. So how many would be parental 1? 37.5, yes. And how many would be each of the recombinants? 12.5, right? So we would expect, and obviously we don't get half individuals, but we would expect to get about 38 parental 1s, about 38 parental 2s, about 13 of each of the recombinants. Does that make sense to everybody? Mm-hmm. Okay. If we have the same 100 offspring, but our recombination frequency is now equal to 50%, how many offspring do we have in each of the parental categories? Yes. 25 and 25, right? Because half of our offspring, we know our recombination frequency is 50. So 50% will be parental and 50% will be recombinant. How many recombinant do we have? Now, if you were testing this group of individuals using our expected 1 to 1 to 1 to 1 frequency or ratio, does this look Mendelian? This looks like independent assortment, right? We don't. Right? So that's this first caveat is if our recombination frequency is high, that means that we cannot distinguish between linked genes that are really far apart, because this would be 50 map units, really far apart on a chromosome, versus genes that are on different chromosomes. Okay, so the further apart they get, the more challenging it becomes to determine, in using this method, if they are linked or not.
Is there like an official cutoff? Or
50%. Yes. So we would say anything that is more than 50 map units apart, we cannot distinguish. Why is that? What happens as the distance between two genes increases? No, so let's say we have, not as much.
There's none?
No. So I'm going to draw 2 chromosomes. Let's see where it's worse. Okay. So we have so we have 2 chromosomes. These are homologous chromosomes. We'll pretend they're in tetrads. If we have a gene here and a gene here, and these are 10 map units apart, and then we have another gene up here, and these are 56 map units apart. And we're talking about crossing over, which is a random event. Where are we likely to get crossing over more often?
The ones that are close together, like the A and B.
We're going to get it more often there, or less often?
More often.
Let's see, last week it has lots of crossover.
Okay. Yes. So this area is fairly small, so the odds of getting a crossing over event in that sort of short area is less than the chances of getting a random crossing over event in this area. It all has to do with just physical distance between them. Okay, because we could get a crossing over event that occurred right here randomly, we could get it right here randomly, right? We could get any number of random crossing over events in this big distance. There's only a few crossing over opportunities in this shorter distance. So, the closer together we have 2 genes, the less common recombinant progeny are going to be. Right? So in this case, with 10 map units, we would get 10% of our offspring being recombinant. That's a pretty small number. Here, with 56 map units, we'd expect 50% being recombinant. Okay, so it has to do with how much opportunity is there for crossing over in this big space versus how much opportunity is there for crossing over in this little space. If we assume that crossing over is kind of random, up and down the chromosome. Okay, and then the other piece, the other caveat, which might be a little bit unclear now, but it's going to make more sense when we're looking at 3-point crosses. We often underestimate the distance between 2 genes if we have, if they're really far apart, because we increase the chance of a double crossover event. A double crossover event would look like this. So rather than me try and draw it, I'm just going to point to a figure I already have. A double crossover event between these 2 genes means that when we look at the offspring, they all look parental. Does everybody see that? Because we haven't changed any of, we don't have a big A and a little b together now. We still have our big A and our big B. We still had crossing over, but it was a double crossover, so our chromosome broke and switched at 2 places. So we do have some change in the genetic information, but it didn't affect the loci that were far apart. So they look unaffected even though they are actually affected. And that changes how we calculate our map distances. Okay. Okay, so we're going to practice producing a genetic map. Here I have set it up for you. So we have fruit flies. We have 2 different phenotypes here for 2 different traits. So we have bristles and body color. 1 parental generation, this is a test cross. So one of our parents is going to be heterozygous for those 2 traits. The other one is going to be homozygous recessive, because we always have a homozygous recessive individual in test cross. Here is the, sorry, this is really hard to see. Here is the F2 generation. So we have 537 long bristled gray bodied, 542 short bristled ebony bodies, and then 76 and 75 of our combined progeny, long bristles and ebony and short bristles and gray. So immediately, which of these are, well, I know it tells you, but which of these would be parental and which of these would be recombinant? Right, so the two on the left are definitely our parentals, first of all, because we know what our parents look like, and second of all, because it tells us. And the numbers are much bigger for these two. So go ahead and calculate. Can everybody see that, or do I need to attempt to make it bigger? I see switching, so I'm gonna, no! I don't know if that helps at all, but. Go ahead and calculate the map distance between the S and E, which are the bristle and body color genes.
She's learning how to help.
It's a good skill.
That's the worst thing in the world.
Yeah, only one we talk to. That'll mess up the register. Yeah, definitely don't do that. I don't work. Good. Oh, you guys are so good at algebra.
Yeah, if only this is what analytical was.
Even more reason to enjoy this class.
Are you sure about that?
With great
The
figures.
rest of this is kind of gibberish.
No. What'd you add? No, so we have to add all of those together. I was reading the total. Yeah, the total for each case. Awesome. Okay, so it looks like most people are there. How would we calculate this? Add up those, the little ones. We're gonna add up the little ones. The recombinant progeny, which is 76 plus 75, and we're going to divide it by.
537 plus 542 plus 76.
You're talking too fast.
I'm just slow in general, so. Yeah? Is everybody there? Is everybody okay? Okay. And then you remember, here's another situation where you have to remember your order of operations. So first we would add, and then we will divide. You laugh at me, but I often see this done backwards. Okay? So I'm going to tell you again. We add and then divide, and you should end up with something around here.
You enter that into your calculator without parentheses. It's kind of
Yes. Your calculator doesn't know what you mean. Yeah, so add and then divide. So 12.3-ish?
Yes.
I don't care about significant figures. Don't tell the other faculty that I said that. They're very important for things that I don't care about. So, I love hearing these things. Get your classes straight.
They know.
Okay, so as a reminder, the distance between two genes is going to impact the frequency of crossing over in what way? As you're going to see this on an exam, as distance increases, frequency of crossover
increases.
Everybody together. As distance increases, Frequency of crossing over?
Decreases.
Increases! That was like maybe 3% of the class.
We were 10%.
Okay, so if crossing over occurred in every meiotic event, what would the proportion of recombinant offspring be? If it happened every time meiosis happened? Yeah, if there was crossing over at the same spot every time meiosis occurred, 50% of the offspring would be recombinant. So we would produce chromosomes that look like this: parental, non-parental, non-parental, parental. So 50%, these two would be parental. 50%, these two would be recombinant. So we don't go over that 1 to 1 to 1 to 1 ratio. That's sort of our max ratio. Okay. All right, so here is a figure that sort of demonstrates this for us. Map units. That's going to be distance between any two genes on a chromosome, and the percentage of recombinant offspring in a test cross. It increases really rapidly until we get to about that 50 map units, and then it increases again. It continues to increase, but not significantly. Okay, so we don't see a significant change after that 50 map units point. Okay, so now I've given you some information. We're going to do this backwards. I've given you recombination frequencies. You can convert those into distances between genes. I want you to draw me a map. Okay, so if I'm asking you what's going on, I have 3 loci here, A, B, and C. I've given you distances between all 3 of those. Oh, I'm sorry, A, B, C, and D. 4 loci. Tell me what's going on. Draw me some chromosomes. Do we have to draw? You can converse with your neighbors and try to figure it out together. Music to my ears. So you have recombination frequencies of 50%.
It didn't make it on my map yet.
So we have there are 2 options here. When we see recombination frequencies of 50%,
I don't know.
can determine that they are either really far apart, that they're on. So the fact that we have A as being 50 map units from B, 50 from C, and it's probably on. So you would have one chromosome that has just A. Yeah, so how would you get, it couldn't be 50 from B and C and D with B and C and D and C. They're all exactly. So yes. Okay, I'm coming around. Oh, good try. I'm not always slow. It's probably on the slide because Dr. Brent does that all the time. I'm so excited. We ask questions and then she puts it on the slide. Yeah, what's going on?
I don't know under
What are we seeing? What are we feeling?
Two big here, be on this thing, but I don't know how
Okay.
they're gonna be on different.
How would they be on the What do you mean? You don't know how they'd be on the chromosomes?
Yeah, like, I don't know, like how like the numbers are gonna be on different ones, like, for this and like,
It would just be
automatically.
yeah, because we can't calculate it. we calculate these based on recombinant progeny, and the most we'll ever have is 50% recombinant, 50% swing, so A. Boom. Look at that, you do now. Alright, how you guys doing? So,
I am A.
for this,
Because I get to go on to
we have sort of two potential options with what's going on with gene A. So either it's really far from all of these, or it's on a completely different rate. So because A is far from B and far from C and far from D, and there's no combination where it gives us anything under 50, we would assume that A is on separate chromosomes. So we would actually be drawing two chromosomes. One of the chromosomes would have our B, C, and D alleles, and the other chromosome would just be A. A sort of
Okay, so it's like, wait a minute.
yeah, because
What was the
right, so when you turn further apart, we have double recombination events that make them benefit together, which is why I
Okay.
don't point that out.
Yeah, the part, you know what? I was trying to.
Yes. Yeah. Right?
Okay.
So, with what you have drawn here, if A would be from B, squiggly, what are the things from? Yeah. So when we're looking at these numbers,
Let's Google.
A so there are kind of two options. If it independently sorts, you would give that same value. Or it could be really far from. Since it is noted as 50 from all the other three, it is based on the assumption that it's on its own chromosomes. It's actually on two chromosomes. One is just A, and the other one would have A.
Well, she might actually allow it. And the track thing, that's what you're.
No, so for the body, we're downloading it. You figure out that it's kind of like the numbers are It's actually not.
Oh,
Unlinked, so we can't. So if we look back at our caveats, one of them was that when two genes are far apart, we underestimate the distance between them because of double crossover. So when we are calculating vector spaces like this, all of ours will add up because we will account for double crossover. But in this case, it's not accounted for, so it looks smaller, it would actually be big. All right. Did everybody kind of figure it out? No. All right, well, let's.
The more you talk about these are people look more confused.
The more I talk about things, the more confused you get.
Yeah.
Excuse me. I will try a different lecturing technique then.
Now, I'm just saying with this thing, because this is some goofy.
Guys, it's going pretty well until we got to this.
Basically. What if I just read the textbook to you in my lectures?
Yeah, my God.
So I
Literally.
Hey, I mean, that would probably be the only way to do it again. People like read it.
Okay, so what do we see if we just kind of want to break this down into groups of genes? What is sort of our big pattern here?
A is equal distance from all the other three.
Right, so the first thing we should notice is that anywhere we have A, we also have a recombination frequency of 50%. Anytime you see a recombination frequency of 50%, you have two options. One option is that A is really far away from everything else on our chromosome. The other option is that A is on a different chromosome, right? Because whether it's independent assortment or really big distances between A and the other genes, we get 50% recombination. Okay. So since in this case, A is 50 map units from B, C, and D, it's a fairly safe assumption that it's on its own chromosome. Okay. So I wasn't trying to trick you, but we do have to sort of think about anytime we have recombination frequencies of 50%, we should think, is this on its own chromosome? In this case, it fits fairly well that A is just on a different chromosome. So we're actually drawing two maps here. A is pretty easy because it's just by itself. The others we have are B, C, and D. We have map unit measures of under 50 here, so it's, again, safe to assume that these are linked. Okay, so these three are linked together. What order, based on this information, would these genes be in? CBD. Does everybody agree with that? Okay, it doesn't matter if it's CBD or D, C. Yeah, as long as, what was the middle one? B. As long as B is in the middle, we could put D and C, or C and D, it doesn't matter because we can flip a chromosome upside down. Okay, so the middle gene is going to be the important one because it can't be on an end. It changes the actual order of the genes then. Okay, so you said B, C, and B, D, and C, C, B, and D. Okay, here it was. Alright, so you should have something like that. And then we can simply take our map distances or our recombination frequencies and label this. So the distance between C and B is 20, and obviously mine is not drawn to scale. It's not centimeters, it's centimorgans. And the distance between B and D is 10 map units, or centimorgans. The distance between C and D is 28 centimorgans. Our map looks like that. Okay, now a couple people noticed that 20 centimorgans plus 10 centimorgans does not equal 28 centimorgans. Yeah? You can do good math.
Sometimes.
Why is that?
Because B itself is.
We overestimate.
We underestimate distances between distant genes because we fail to account for double recombination, double crossover. So they would actually probably be closer to 30. But when we just look at it and use our offspring to figure it out, it looks a little bit closer together. Alright. Ta-da! Yes?
So we can use MU and CM interchangeably?
Yes.
You don't care?
Yes. As long as if I ask the question, how do we measure map distance, you don't tell me centimeters. Laugh.
Just write M.
This is like my own personal hell when I see these things. What?
Can we just write MU?
Yep. Yep. Whatever your preference is.
I like that more.
Okay. So we are going to start getting into how we predict outcomes with linked genes. I'm going to just give us an example and sort of walk us through it, and then on Monday we will go through 3-point crosses. 3-point crosses will be what you do the most of, and it is, so at this point you should actually be able to do about half, actually you should be able to do, yeah, almost exactly half of chapter 5's homework. The other half we will talk about on Monday, and we'll be set to go on the rest of it. Okay, so we go back to our friend Thomas Hunt Morgan, who kept flies by his bedside so they didn't die. And he looked at 3 traits: body color, eye color, and wing length. And he came up with this, right? So he did crosses with these. And he came up with this F2 generation. So automatically, when you're looking at this F2 generation, what do you notice about the frequencies of the offspring? Okay, first of all, it's not one-to-one. We are actually dealing with 3 traits here, so we have a very weird ratio. We have eight potential phenotypic outcomes.
And there's one that never occurred.
Okay, so we have 1 that never occurred,
One that barely occurred.
1 that barely occurred,
Some that occurred a lot.
some that occurred a lot. Okay, we can go ahead and look at this and actually start breaking apart what is what. So we have 2, if we go back to the last slide and we look at the parental generation, we have an individual that's yellow, I forget what we stand for, white-eyed and miniature winged, and then we have a wild type that is red-eyed, gray-bodied, and normal winged. Okay? So when we are looking at these F2 offspring, where do we see the parentals?
The way top and way bottom.
The way top and the way bottom. We know that again 2 ways because we can read them. Gray body, red-eyed, long wings. So this is one parental. We also know that we also know that it is the biggest phenotypic class. This one is the other parental because it is also big and is the phenotype we saw in the other parent. So since I guess I should go back. We know that these are linked because all 3 of them occur on the X chromosome, so there's no way they're unlinked. So this was kind of his experiment. And they would be transmitted as a unit. So without crossing over, the only 2 phenotypic outcomes we would get would be this one and this one. But we have seen now that crossing over did occur because we have these other phenotypic crosses. So we can start picking out other things. We can actually group our next 2 biggest, so gray body, red-eyed, miniature wings, and yellow body, white-eyed, long wings, as a single crossover, and I'm going to call it single crossover 1 and single crossover 1. These 2 are another single crossover. Remember, we're dealing with 3 genes here, so we can get a single crossover at one place that would impact phenotypes, and a single crossover at another place that would impact phenotypes. And then these 2, which are very rare, are results of double crossovers. Double crossovers. So, just looking at the 4 single crossover events, does it look like one occurs more frequently than the other? Yes or no? Yes, single crossover 1, we have fairly big numbers of. What does that mean about the distance between the 2 genes involved in single crossover 1? They're further apart than the 2 genes that flip in our single crossover 2. Okay? All right, we will come back to this and we will figure out the rest of it Monday, and you'll be set and golden on this chapter. It'll be beautiful. It'll be so beautiful. When it comes together, it just like clicks, and all of a sudden it's like magic. Sorry, I should know better than to get on the side of the class. You get a chance to work on it.
I just got my email, they denied my parking pass thing, so now I have to pay basically $80 for a parking pass because they didn't give it to me.